Okay, ready? Let's go. Like I said, we're going to start something new today. We are going to talk about linear inequalities. And ultimately, the main topic we want to talk about is linear programming. But we need to know about linear inequalities in order to do linear programming. We're going to be doing mostly a geometric view here, so that should be a little fun. There are ways that we can do things computationally, but geometry is going to be the focus here. Let's actually talk about what these are. A linear inequality in two variables. We're only going to be dealing with two variables. This one of the forms ax plus by less than c, ax plus by less or equal to c, ax plus by greater than c, ax plus by greater than or equal to c, where x, y are variables and a, b, c are constants, with a, b not both 0. See anything like that? It is called a linear inequality. We can talk about if we were to sketch any of these in the XY plane, it would there's the idea of a half plane. If you sketch a linear inequality, you will divide the plane into two parts. Each part is called a half plane. And the solution to the is the set of all points in half plane that makes the inequality true. So you draw one of these guys. They're actually going to look at exactly like the equation of a line. I'll talk about what the differences are. But we're going to slice the plane into two parts, and basically the idea is we want to know which part is going to be our solution. One of the half planes will be a solution, all points in the half plane. How do you know where the solution is? Well, this is the half plane that contains all the points that will make the inequality true. I'll talk about that pretty soon right now. To sketch the solution. One, you're going to just sketch the line. Just imagine that the inequality sign was just an equal sign. Usually the easiest way to do this is going to be to sketch the intercepts. You only need 2 points for a line. I should probably mention that. I don't want you to waste your time plotting like 7 points or something. You only need 2 points. The x and y intercepts are usually the nicest points. And as you might recall from algebra class, the x-intercept is the x value when your y equals 0. The y-intercept is the y value when your x equals 0. So if I wanted to sketch, if I have a line and I want to figure out what is the x-intercept, I'd imagine y equals 0, solve for the x. What is the y-intercept? Imagine x equals 0, solve for the y. I can plot these 2 points on the axes, and once I have these 2 points, I just connect them with a straight line. We'll actually do this pretty soon. The line style is important. In the sense that if you have a greater than or less than strict inequalities, we call them strict inequalities. Then the line style is going to be a broken line. If you have non-strict. So that greater than or equal to or less than or equal to, then the line style is a solid line. So how you sketch the line is going to be important. So this is going to mean that the line itself is not included in the solution. The points along the line does not form a solution. However, if you can be equal to the line, you draw a whole line. Now, the third thing in sketching the solution is now 3. You want to shade the half plane. That contains the points. That made the inequality true. A couple ways you can do this. Method 1 is to simply plug in a random point that you know is in one half plane. So you're going to take a point that you know is in one of these regions of space. You're going to plug it into the original inequality, and then you're going to just assess whether or not it's true. If the point works, then shade that half plane. Doesn't, shade the other one. We're going to do some examples pretty soon, so don't worry, I just want you to have an idea of what we would be doing. And method 2 for accomplishing this. Solve for x or y and shade according to the following criteria. So you can solve for x or y. So you can have, say, x is greater than by plus c or some version of that, or greater than or equal to by plus c. You can also have x is less than by plus c, or less than or equal to by plus c. You can solve for the y greater than ax plus c, or greater than or equal to ax plus c, or y is less than ax plus c, or y is less than or equal to ax plus c. And each of these goes along with a certain position. So if you solve for x and you end up with this position, x is larger than blah, or larger than or equal to blah, you shade to the right. If x is less than blah, or less than or equal to blah, shade to the left. If your y is bigger than blah, or bigger than or equal to, shade on top. And if it's less than or equal to, shade on bottom. So we're going to throw shade according to these two. One of these two mechanisms. Okay. Kind of, you can pick the one that you like more. Let's actually just do some examples now. Sketch the solution to the following. Let's say y greater than 1. It's less than 5c. Times 3y greater than 6d. X plus y less than 2. It's minus 5 greater than 0. We're going to sketch each of these. Okay, let's see. Some space here. Stop here. So let's go over this. How do we sketch the solution to these inequalities? This is a linear inequality. Notice it follows the definition. A is 0, B is 1, C is 1 in the greater than sign, and similarly all these fit the definition. Now, pretty much if you want to sketch the solution to y is greater than 1, first thing what you do is you'd actually sketch the equation. Sketch y equals to 1. And what does y equal to 1 look like? Yeah.
A flat line.
Just a horizontal line going through 1. And notice because this is a strict inequality, I'm going to draw it as a broken line. Going through y equals 1. Now, I want y greater than 1, which means this actually falls in line with method 2 very nicely. I see that y is bigger than something, so what do I do? Shade above. I'm going to shade above the line. So that's the solution here. Another option that you could do is, again, you could plug in a specific point. Make sure that you know for sure the point that you're picking, which location it's in. So I could pick, for example, this point here. This is an example. So I could say something like this is 0, 2. And so if I use 0, 2, I could say, well, this means that my x is 0 and my y is 2. Now, if y equals 2, well, that's actually larger than 1. So then, yeah, that actually works. That point is in the solution. If, on the other hand, I had picked another point, like, say, the origin, which I know is down here, 0, 0, then what I would end up with is, if I pick 0, 0, this would mean that my x is 0 and my y is 0. And if y equals 0, I ask myself, is that greater than 1? And the answer is no, this is false. So had I picked the origin and tested this inequality, I'd realize, oh, that doesn't make sense. Which means the solution is the other side of the line. It's the other half plane. So you can either pick a point, or depending on how it looks, if you solve for the y, you can shade on the top or the bottom, depending on what should be most convenient. Doing a very similar thing here, we have x less than or equal to 5. So what you're going to do is pretend you're going to graph x equals 5, which is just going to be a vertical line, solid line passing through 5. Now, because I know I want less than or equal to 5, this is in a nice form for method 2. I'm going to shade to the left. I want all x values that are less than 5, so x equals all of those guys. So this entire region here is going to be the solution. Every coordinate that I pick over here will work with that inequality. That's the difference between broken lines and straight lines. Hopefully that, how do we do this one?
You can solve it to get x is less than or equal to u plus u half.
Yeah, but how do you actually get the picture? How do you put the graph down? Yeah, I know you just graph it, but how?
Just graph it, just do it.
Right, if you plug in 0 for x, you solve for y, right? So that would mean y equals what? -2. So I'm going to plot -2 on the y-axis. Right? So if x equals 0, this means that your y is -2. So I plot that on the y-axis. Now I do the same thing for the opposite. If I plug in y equals 0 and solve for x, I would get +3. So I know y equals 0. This means that my x equals 3. So I plot those 2 points. Now for a straight line, you only need 2 points, so I'm just going to connect these points with a line. And that is an unbroken line because it's greater than or equal to. So it's a solid line, just going like that. And now I want to know who can I pick to actually, which region should I pick? The solution is either going to be over on this side of the line or on that side of the line. The line is going to split the space into 2 regions called half planes. Only one half plane at a time can be a solution. So again, we could do something here, like if we solve for x, we would end up with x is greater than, say, 6 plus 3y over 2. Right? So because x is bigger than something, if I decided to solve for x, I know that the solution should be on the right side. Another way, the origin is a nice point to pick a lot of the times. Notice if I choose the point 0, 0, plug in 0 and 0 here, I get 0 is greater than or equal to 6. That is false, which means, again, the solution must be on the other side. So, turns out over here is the solution. This entire half right here. Similarly, for x plus y less than 2, if I plug in y equals 0, I get x equals 2. If I plug in x equals 0, I get y equals 2. So that's just a broken line. Passing through there. Now, if I pick the origin 0, 0, 0 is less than 2, so I know that the solution is over here. In the bottom half. I could also solve for y, for example. I'd get y is less than 2 minus x. Less than means it's to the bottom, it's underneath. Don't have a lot of space for this one here. Let's put a bit over here. X minus y is greater than 0. Now if we look at this one, now if you plug in x equals 0, you get y equals 0. Plug in y equals 0, you get x equals 0. So this only gives you 1 point looking at that. There are a couple ways you can sketch this one though. One is to plug in another random point. You'll notice that if you plug in x equals 1, your y would also give you 1. But you could also realize that if you were to write this as an equation, x minus y equals 0, then it's just the line y equals x, which probably should know that that's just a line going through the origin at 45 degrees. But either way, once you have 2 points, you can plot the line. It's not solid. So it's going to be your line. Remember, there was a professor that I saw that had a really cool way to draw a broken line. It's like I don't know what he did, but he holds the chalk at a certain angle so that he just does this and the chalk just skips across the board. And I don't know how he does it. I've been trying to figure it out forever, and I just end up drawing solid lines. So. But when he does it, it's just like, I don't know. I'll figure it out one day. Yeah, so broken line going through the origin, and again, a couple ways you can do here. I can pick a position where like 1, 0, and that would actually work, so that give me that. Another thing is I could solve for the x, I'd get x bigger than something, which means I should be to the right. In either case, the solution is over here, in this half. Questions on this, how to get it done? Yes, that's pretty much it. No, that's not it. We're going to... Here's the thing though. You'd have to be able to do this for multiple things at the same time. That's kind of where we're going. And then once we can do this for multiple things at the same time, we're going to throw an application on top of it. So what we actually care about is not single inequalities. I want to talk about systems of inequalities. So now you know how to deal with one of them at a time. How do you deal with multiple of them? So if I give you a list of inequalities that I want to satisfy all at the same time, how do I figure out how to actually do that? System of inequalities. This is just several linear inequalities considered together. The solution is the region of space solves all systems, all inequalities in the system. At the same time. Pretty much the process for getting this done. Solve one at a time, find the overlap. And now here's some more vocabulary before we do some examples. The solution space here is called is the solution space. Right? That's just a set of all points that will make it true, or sometimes it's called the region of constraints. That's more like a linear programming idea, but we'll get to that. Or sometimes it's called the feasible region. Kind of depends on context when we use it. So we might say the solution region, or the region of constraints, or the feasible region. These are all referring to the same thing. Solution region. These all refer to the same thing. It's just this. It's just the section of 2D space that makes all linear inequalities true at the same time. And basically, what you're going to do is what I just showed you to do. You're going to do all of them at the same time and find the overlap. Find the region of space where all these solution spaces intersect. Let's do this. Any questions on that so far? Example, solve the following. Solve A. Solve B. Start with those two. Same kind of thing, but I'm just tweaking a little bit. I'll flip this here because I want to introduce another definition. So here is what we're going to do. Sketch the axes here. Okay, what I'm going to do is I'm going to sketch one at a time and find their solution. So if I sketch the first one, x plus y is less than x plus y equals 2. We actually looked at that before. That's going to be a line with negative slope. It'll pass through 2 here and 2 here. Let's label it because so that we don't get in trouble. So I can label this x plus y is less than 2 or equal to 2 if I wanted to label that. And now I want to shade the solution region to that. So where is going to be the solution region? Yeah?
Below it.
Below it. So I'm looking at this. then I'm going to do x equals 0. Now x equals 0 is the y-intercept, the y-axis. And it's actually equal, so I can draw a solid line just right on top of the y-axis. And I want it to be greater than 0, so the solution there is going to be everyone here. So line x equals 0. Then I'm going to look at the line y equals 0, which is the x-axis. It's going to be this. And I want y to be greater than or equal to 0, so that is going to be everything above. And now what I want is the actual overlap. So I want to pick out the region in space that actually solves all of these at the same time. And of course, as you'll recognize, it's going to be this little triangle here, not including the boundary up here. That's going to be the solution. So I just do them one at a time, and I find the overlap. Now, sometimes just having everything shaded might get some people confused. So what you can do instead, or indicate solution of each by arrows. So sometimes people like to do that. So if you had this, then you would have one line going here, one line going here, one line going here, and then you might just say, okay, for this line, what's the solution? Well, I want it to be less than 2, so it's going to be, draw arrows going on it here. So you can just imagine that I'd be shading down here, and for this one, the solution is going to be going towards that direction, and then for this one, the solution is going to be going up. So then you kind of say, okay, I want to shade to the right, I want to shade up. So you can already see an intersection here. It's going to be in this region over here. Then when you look at this line, you know I want to shade down, so it ends up being this region. And these should not be. So this is called the feasible region, or the solution region. Any questions on this? Okay, quickly do the other one. Where is he going with this? Going someplace good. You'd be amazed all the kinds of problems that we can actually solve with this. The actual theory behind it isn't that bad, so it's just a matter of actually getting in and doing the specifics. Once you're not doing linear, it becomes a lot harder. And then when you have more than 2 variables, that becomes a lot harder. You probably have to know like Calc 3 to start even doing that stuff. But with linear in 2D, it's not so bad. So very similar thing going on here. I literally just swapped one of the sides. So I have that. I have that. I have that. At least I have. So now, it turns out that we have a lot of spaces. So let me kind of list these guys off here. So there's region 1, region 2, region 3, region 4, region 5, region 6, region 7. So 3 lines are going to cut this guy into all those regions over here. Where is our solution?
What?
Region 1. So here I want the x plus y to be greater than 2, so now I'm going to be going up here. I want to be greater than x equals 0, greater than y equals 0. So the solution is going to be in region 1. That part over there. Now, again, just by tweaking how the inequalities actually behave, we actually get very different looking feasible regions. There are actually some general terms for these ones, which I'll define. This region here is called a bounded feasible region. While this one is unbounded. What those mean. It is a phrase or unbounded. And bounded, this means can be contained. In a circle of finite radius. So it's possible for me to draw a circle and contain this entire region. In fact, this goes through 2 and 2. So I can put a circle centered at the origin, radius 3. That circle is going to contain the entire feasible region. This, therefore, is a bounded feasible region. Unbounded means you can't. You can't do that. So if you were to look at this one, no matter what radius I open a circle to, there'll always be points outside the circle. The circle that would capture this entire region has to have an infinite radius. So we call this unbounded. That's the difference between bounded and unbounded regions. And they might behave differently in certain situations. One thing we want to do, another thing that I want to do it to. The intersection of the drawn lines are called corner points or vertices of the feasible region. So if I talk about the vertex of the vertices of a feasible region or the corner points, that's what I'm talking about, where the lines actually intersect. Vertices is plural for vertex. So here, for this feasible region, there are 3 vertices. There's one right here, there's one right here, and there's one right here. It's where any 2 of the lines intersects. probably it's better to phrase it that way. The intersection points of any two. So you don't need all three lines intersecting, but once any two lines intersect, this creates what we call a vertex or a corner point. So that's bounded, unbounded vertices and corner points. So, any questions so far? Do these examples. And this one.
Is that supposed to say what is?
Here?
Yeah.
Yes. Again, the same idea, so you can draw almost the same picture, but the way the inequalities are turning are going to be different and would yield different situations. Just want you to be aware of all things that can. A single problem can have several different scenarios, and basically, sometimes you're going to have to figure out these inequalities from like word problems, so you have to be careful how you're reading them, because if you read something as a greater than when it should be a less than, you can end up in a completely different situation. It can go from an unbounded region to a bounded region, or vice versa, and yeah. To do these five very quickly. The first one should take you a little bit of time, but the others you should be able to tweak very quickly based on the first one, so we can actually jump into the next section. I'll give you maybe 6 minutes here, draw a different picture for each.
What's the difference between C and D?
Greater than, less than, greater than. I actually did all possible arrangements of this. Greater than, less than, greater than, less than. So I think this should be less than, less than. Two more minutes. Let's do this. So yep, let's focus on A here. Yep, so draw axes. What does the first line look like? How do I figure it out? Huh? Yeah, okay, so how? X-intercept would be? 6. Plug in y equals 0, solve for x, I would divide both sides by 2. So it gets 6. 6. And the y-intercept? Plug in that, you get 4.
Just which axis?
It should be the other years.
6 should be on the x-axis.
6, 4. And so we're going to connect these two. That's usually a straight line. It's hard to get it straight on our big board. Okay. So that's one of them. Then you move on to the second one. X plus y, plug in y equals 0, solve for x, you get x equals 5. Plug in x equals 0, solve for y, you get y equals 5. So I need to connect these 2 points as well. So that's going to look like. So you have like this little x thing going over here. Now, what is this location here?
Quarter.
It's called a corner point. What's its location? So figure out the triangle, the vertex of this triangle here, or whatever the thing you want to call it. What you kind of want to do is you need the solution to a system of equations. So, take 2 rho 1 minus rho 2, or the other way, just make it nicer. Rho 2 minus 2 rho 1. This minus t times that, this minus t times that, and this minus t times that. So 2, get y equals 2, which means that x plus 2 equals 5, which means that x equals 3. And so this location occurs at 3 on the 2. Now being able to find the corner points is going to be a very important thing. So finding the corner points is really you setting up a system of equations. Now the other ones are x equals 0 and y equals 0. That's going to be here, here. Yeah.
On exams, like, do we need to label that? On exam?
Do you need to what?
If there's a question like this on the test or an exam, like, do we need to label that? Like, if it was just like graph the inequality, do we need to like find that intersection?
Yeah, because I'm not going to ask you a problem where all you have to do is graph the inequality. We're building up to the kind of problem I'd ask you, right? And for the kind of problem I'm going to ask you, you're going to need to know what these values are. So they're going to be meaningful in a larger context. So yeah, where is our solution region for this situation? I know I want to be to the right of this and above that, so I know I'm in the first quadrant here. You remember that term from pre-calc class? But where in the first quadrant? Well, I want to be greater than this line, and oftentimes it's going to be important for you to label these so you don't get them mixed up. So I would probably label this as the 2x plus 3y equals 12. Label this as the x plus y equals 5. But the thing is, I want to be above both of these lines by using one of the other methods. So the solution region here is an unbounded region. It doesn't go over here. That's stuck in the first quadrant, but above both lines at the same time. So that's what your answer should have looked like for the first one. Questions on that? Okay. So for B, I think we move this to less than. And that is going to change a lot. Let's just start from scratch. So I have the axes here. I have 2 lines. That. That. And this is going to be at 3, 2. This is going to be at 5 and 6. And this is going to be at 4 and 5. And then we're going to have this, and then we're going to have that. Okay, where's my solution region now? So we have a bunch of these here. Region 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 regions here. Which one's our solution? Huh? 6. Okay, so this here, slightly so I don't get mixed up, this is x plus y equals 5. This is 2x plus 3y equals 12. Now I want to be above this line, but at the same time below that line. And so yeah, 6. I also want to be above the horizontal and to the right of the vertical, so that's my feasible region for this one. So your answer to B should look like that. In C, I think we did. Greater than and less than. So what are we going to have here? What's the region here? Huh?
I think it's 2.
So I want it to be above this line here, but at the same time less than this line here. Yeah, 2. It's going to be this region right here. So, and you can double check. It's to the right of this, it's above that, it's below this, and it's above that. That's the region that fits all of these at the same time. So that should be your solution to C. At D, I think we need less than. So and what's this one? Region 5. So your answer here is going to be that. It's going to be very important for you to be able to identify which region gives your solution. And the second thing is going to be noticing what are the corner points that surround that region. You're going to be able to need to find the location of all these intersections. So in a problem that you would be doing, it will be very important for you to identify this region, but as well identify the coordinates of all these intersections. There will be 4 points that will be important to you in the context of the problems I'm going to be doing. So first, identify the region, identify all the corner points surrounding the region. This will be 2 steps in to be able to solve the kinds of problems that we're going to look at. For E, we took out these guys, and I believe this was greater than, yes. So the graph is going to just have 2 x's, not the vertical and horizontal lines. So you can get a lot of use out of this like one picture. So that's going to be 3.2, 5 and 6. This is going to be 4 and 5. There are no vertical or horizontal lines. What's the region now?
It was 2 and 3 in the last picture, so it's region.
So region, right, I labeled them 1, 2, 3, I think. So you think it's 2 and 3? Yeah, we want to be above this line here, but at the same time we want to be below the other line. And so yeah, this is that. So that infinite triangle going off that way. In the above, I don't remember what order we did it in. In the above, what parts gave you a bounded solution and an unbounded solution? Well, for sure, E gave us an unbounded solution.
A was on
A was also unbounded. Everyone else was bounded. That we did. Yeah. So, being able to identify the feasible region, knowing if it's bounded or unbounded, identifying the corner points. These are all important skills for us to know. Okay, let's go to why do we need to know all this? I believe that is the introduction. And it's surprisingly applicable, especially in business context. I mean, one of the reasons I like teaching this is that I don't get to do it very often because I don't do business math, I do pure math. And it's like kind of fun just drawing pictures and shading. You just slow it down every now and then. But linear programming is a thing that is very important, very applicable. So there is an idea called optimization. This basically means make something as good as possible within certain constraints. Mathematically, this often means maximizing or minimizing some function. Constraints. Now, in calculus, you'll learn another version of this optimization, and there'll be others that you will learn in other classes as well. But for us, we're going to do linear programming. And basically what this means is that, so linear programming. What is actually linear programming? This is the process of optimizing a linear function where the constraints are given by systems of inequalities. Now, once we're not doing linear on a linear constraint, you quickly need calculus or more sophisticated mathematics to deal with that situation. But for the linear cases, we can solve these guys by actually drawing pictures and finding corner points and things of that sort. So this is the situation. There is something that you care about that when you actually map it out, it's a linear function. And it turns out the things that are constraining you are also linear functions. How do you make things as best as they can possibly be within these constraints? So you can be like, oh, I'm a manufacturer. I have this many employees. We can put out this many products per day. If I really push them and give them overtime, we can do this many products per day. I have to pay them this much. The profit I'm making is going to be given by this function. How can I make sure that I have the maximum amount of profit possible given that I have these costs, and this is I have to pay for rent, and this is what I have to pay for employees, and this is what I have to do here, and here's how many products I can make per day, and here's how many I can sell per day, and blah, blah, blah. Turns out a lot of situations like that, business situations, a lot of these things that are involved, you can actually map them as linear functions. So there'd be one linear function that you really care about, and that's the one you want to maximize, like maximize profit or minimize costs or something like that. But then there'll be a bunch of other linear systems that really describe the restrictions that you have. Well, I can't produce more than this in a day, and so that kind of is a restriction there, and so on and so forth. So once you want to maximize or minimize a linear function within a context of linear constraints, we say you are doing linear programming. That's what it is. And we'll be doing the graphical approach. There are several approaches. The simplex method is a pretty popular one beyond this, but we're not going to do that in the graphical approach. The function we want to optimize is sometimes called the objective function. Next time I think I'll start with an example like this. Here's what we're going to do. I have a function of x and y. It's going to be linear, so it's x plus 2y. And I want to maximize f. Given that 2x plus y must be less than 22, x plus y must be less than or equal to 13, 2x plus 5y must be less than 50, and my x and y need to be non-negative. So here are my linear constraints. I need to satisfy all of them at the same time. These are all the things I have to worry about, you know. Overtime pay, costs, rent, blah, blah, blah. I have a bunch of things to worry about, but really I want to focus on one thing. For this quarter, we need to get our profits to be a certain way. So we have all these things going on, but there's one thing I really care about at the time. How can I plan to make that as good as possible? So the next time we're actually going to do that. And we'll use this to illustrate. See you guys on Thursday.